Yeah, it's a pleasure to be here. Thank you for this opportunity for me to come and discuss what we are trying to do in the deep Mediterranean Sea. So the talk is going to be about neutrino astronomy, neutrino astrophysics, but I suppose you know already quite a lot about it. I will not make a review on everything that's happening, so I will not discuss much about ice cube or other detectors, and I will concentrate to the Mediterranean. But of course, I can answer questions. We can also make it interactive and lively. So if you want to interrupt, ask questions, please don't hesitate to do so. And let me try to start. Uh, Technical issue, but I will manage for the. Okay, yeah. So this is what I foreseen to discuss today. So I will go a little bit into the general purposes of neutrino detectors, neutrino telescopes, and then I will discuss selected results. So I think that you're probably eager to hear about the KM3 special event that we have measured some time ago, the most energetic neutrinos ever seen on Earth in principle. And then if I have time, because I'm always a bit too long, I will discuss about the prospect of the low energy branch of KM3net that we call ORCA, and that is primarily meant for the measurement of the mass hierarchy. So I think today's picture of neutrino worlds, you probably know. I'm not sure exactly what's the audience here, but I have only one slide to tell you about neutrinos. There are very special particles. I guess that you're convinced. We don't really know what they are actually, if they are their own antiparticles, and so other experiments are dealing with that. Obviously, we don't know how they acquire their mass, and if it's the same as the others. We don't know whether are Dirac or Majorana particles. We do know that they have masses, tiny masses, a million times at least less than the other massive particles. We know that because they oscillate. I think you're well aware about this here at this McDonald Institute. And so we have made measurements of the parameters of the oscillation matrix, the mixing matrix, to a fair precision, but there are still some of the measurements that we would like to do, and in particular, we would like to know what is the mass ordering, and this is really what we are targeting with ORCA. So the mass ordering is essentially, we would like to know whether M3 is the lightest or the heaviest of the three neutrinos. The other two are already ordered, if I may say so, because of matter effects in the sun. So it's pretty much knowing about this and this ordering. That's important, of course, because, you know, neutrino physics is a kind of a puzzle. You want to put your piece here and you want to know whether this goes into an overall scheme where there could be, for instance, underlying symmetries or things like this. So I cannot motivate that very much from the theory point of view. There would be another seminar, but this is clearly on the agenda of the major experiments. And we hope that we will be able to make these measurements, if not before the others, at least in parallel to the others, or in synergy with the others. There are other measurements that we would like to do, and we would like to better measure, we would like to know what is the octant of theta 2-3. That means whether theta 3 is greater or lower than 45 degrees. And of course, other measurements are tackling the idea of measuring CP in this domain. That's key measurement also in conjunction with you know, the fact that matter, our universe is made of matter and not antimatter, and where it has gone. But this is the general purpose, and here I'm going to concentrate actually on using neutrinos as astrophysical probes and doing astrophysics with neutrinos. And most of the motivation is summarized on this scheme that I took from Francis Halsen. So here you see, and you probably took it from someone else, but anyway. So this is the energy that you see on the x-axis, and this is the distance. And so what we claim here is that if you would like to study the sky at very high energy, it becomes opaque with photons at high energies, and typically at 10 to the 15 electron volts, then the typical distance is the center of our galaxy, to the Earth. So that's very short local scale. And so if you want to study the sky at high energy on over large distances, neutrinos are ideal probes to do that. They are not the only one, because gravitational waves can also play a role here, and that comes into the overall scheme of multi-messenger astrophysics that we are advocating for today. And I do believe this is going to be revolutionary in the coming century. So I think that neutrino physics should be envisaged as part of the multi-messenger astrophysics that we are trying to do nowadays. So neutrinos, they have some advantages and disadvantages. And the advantages is that since they don't carry charge, electrical charge, they are not deflected by the magnetic field. And so you can do astronomy with those. They point back to the sources. Also, they travel almost with the speed of light in vacuum. And so you can try to search for coincidences with electromagnetic signals or with gravitational waves as well. So this game of multi-messenger astrophysics is easier to play with messengers of which you know the velocity. They do interact with matter, but very weakly, only weakly, and that's why they can be used to probe the inner side of the bodies, so the core of astrophysical bodies, and travel cosmological distances because they don't interact that much. Of course, because they don't interact that much, they are very difficult to catch, and you have to build huge detectors to capture some of them. Another important thing is that they are produced together with the interaction of cosmic rays. Cosmic rays are nuclides, and there could be protons or heavier nuclides. And this is why detecting neutrinos is also detecting sources of cosmic rays, which we don't very well know because they carry electrical charge and they are deflected by the magnetic field. And therefore, this is one of the original motivation. And so this is the common sketch of how to produce neutrinos in different contexts, but that's always the same. So if you're on Earth, you want to have a neutrino beam, then you will shoot photons on a target and you will create pions or kaons, and those decay into neutrinos. And this is how you get your neutrino beam. This is the same for astrophysical body. So what we think is that particles are accelerated in astrophysical bodies through shock waves, for instance, and then they will interact with the material or with the ambient radiation to produce again those pions decaying into neutrinos. So again, the same phenomenon. And the same, and so this is why if you detect a source, then you detect a source of cosmic rays, because those cosmic rays accelerated close to the source will produce neutrinos. If they're not interacting before and then they reach the Earth, the cosmic rays will interact in the atmosphere and they will produce, with the same phenomenon, the same mechanisms, what we call atmospheric neutrinos. And atmospheric neutrinos is going to be a background, irreducible, for the search of cosmic neutrinos, but it's going to be the signal that we're studying for the measurement of the mass ordering of neutrinos, searching for oscillation of atmospheric neutrinos through the Earth. And then I'm also mentioning this cosmic ray proton coming and interacting along its way to the Earth with CMB photons and producing again pions which will decay into neutrinos. So again, the same phenomenon, but this time we call those cosmogenic neutrinos, and they have higher energies because of the low energy of the CMB photon. You have to have extremely high energetic photons to create the pions, and therefore you have also very high energetic neutrinos. And the reason why I'm mentioning this is that we believe that the very high energetic neutrinos that we have detected with KM3net is possibly the first cosmogenic neutrinos detected. So that's for the mechanism of production of neutrinos. And then, of course, we have a series of potential sources that may emit neutrinos. That could be sources extragalactic, like active galactic nuclei or galaxy clusters, or even gamma ray bursts. But this has been constrained very much already by IceCube. But there are still models where you could expect some neutrinos. And then you may have sources closer to us in the galaxy, for instance. So that could be microquasars or supernovae remnants. And so we're also eager to scrutinize the galaxy with neutrinos. Of course, there are other potential sources, and there are sources that might not be astrophysical, and that also could be coming from particle physics. I will not have time to review that much into detail, but I may come back a bit about that. In short, what is the mechanism for detecting those neutrinos and the principle? So this is summarized here. So you imagine you have a source here. You have all these probes emitted. Neutrinos go straight. They come to the Earth, and they can make it through the Earth. But eventually, they can traverse the Earth and interact, usually by charge current interactions, but maybe also by neutral current interactions, close to your detector. And so depending on the neutrino that it's incoming, whether it's a muon neutrinos or a different type of neutrinos, you may have two different topologies in the detector. The first one is when you have a muon produced, and then the muon goes through the detector, and then it produces a Cherenkov light. So we call it the track topology. And if you have other species of neutrinos, they could, like an electron neutrinos could produce an electron. The electron will travel a short distance with respect to the different photomultipliers of your detector. And so you will rather see a bright point that we call a cascade. And cascades may also come from any neutrinos interacting by neutral currents and producing a hadronic cascade in the detector. But the basic principle is that you detect light, essentially in the optical or UV, and then you reconstruct the topology and the trajectory, the incoming trajectory of your particles. And so we believe that both for tracks and cascades, we achieve a better angular precision in water than in ice because of the transparency of the medium. So since you detect Cherenkov light, then you don't want your light to scatter too much if you want to have good precision. And so an example of that is a simulation of a high energetic muons in a same detector but in water in the ice. And so whenever it is red, it means that it is the early time, so the light has not scattered much, and so you essentially see direct photons, while when it's colored differently than red, it means that it has scattered. And that's the reason why there is essentially a factor of 5 in terms of angular power of pointing. Pointing is not a proper word because we don't point the detector, it's open, but power of resolution. Right. On this scheme, you can also see that, of course, since you're going to detect charged particles in the detector, you may have a lot of background, and this background will essentially comes from atmospheric muons, because you detect muons in your detector, but those are downgoing events, meaning that at first you will focus on trying to detect upward moving light fronts. And so that means that if you have your detector in the northern hemisphere, you will focus on the southern hemisphere sky, and vice versa. That is not completely true. In fact, if your detector is large enough, you can also search for signals that are downgoing, but you may need to have a specific method to take a look at inner interactions. And that means that your range of energy sensitivity will be different. Essentially, you cover different energy ranges depending on the angle you're looking at for your particles. Okay, and then of course, even if you restrict to upward moving fronts, you're going to be left with atmospheric neutrinos having been produced the other side of the Earth. And for distinguishing those atmospheric neutrinos from the cosmic neutrinos, it's going to be pretty difficult. And these are the methods that we use. So first of all, you expect to have an increase of events, an excess of events at high energy, because the spectrum of atmospheric neutrinos is pretty steep, while the expected spectrum of astrophysical sources is harder. And so you expect to see an excess at high energy, and that has been the first discovery made by IceCube of a diffuse extraterrestrial neutrino flux, having seen an excess at high energy. But you can also search for anisotropies. If you, for instance, search for a source, then you expect to see a cluster of events in the direction of your source, while the background is essentially, if not isotropic, at least homogeneous in direction. And so, in fact, you search for anisotropies to identify the sources. And therefore, we shouldn't call atmospheric muons and atmospheric neutrinos background, but foregrounds, because they come earlier. But this is the way we speak. And then last but not least, you may find for coincidences in time and or in space with other probes in order to sign the cosmic origin of your neutrinos. And that's the multi-messenger approach that we're also contributing to. Okay, so today's picture of neutrino telescope, of course, you know about IceCube, obviously, the largest, biggest, most successful telescope in the world, and that has been upgraded recently. I'll touch a slide about that. And then other efforts are concentrating in the northern hemisphere. So in the Mediterranean, we have been running and exploiting ANTARES for more than 15 years. So this was really a first generation neutrino telescope. And I will tell you about the story of ANTARES a little bit. And now the next generation with respect to ANTARES is called KM3net. And it's going to be a larger, way larger detector than ANTARES. And the construction is ongoing. There are other efforts in the world. In Russia, unfortunately, it's difficult for us anymore to travel, to work with Russian colleagues. But they are developing their detector on a good path as well, and they are almost reaching the size of a kilometer in the Lake Baikal. And then there are other efforts, of course, in Canada, you know about P1, you know better than I do, I guess. And then there are efforts in China as well, ongoing efforts, several of them. So I can cite here Trident, Hunt, and Neon. And I think that at some point, probably one major experiment should come out in the landscape of China. But okay, in terms of constructions, now really it's essentially KM3net and IceCube. So IceCube, I said I'm not going to mention, but still I have to tell you that IceCube is the largest detector. The current, so it's a kilometer-sized detector. It has been upgraded recently, and probably, but before I touch that, I just want to say it's a shame. In one slide, all the phases that have been reached with IceCube. It is pretty amazing since the beginning of the ideas. The first construction of the first, the first phase, which was called Amanda. Amanda has pretty much the same size as ANTARES, but it was running less time. Then, of course, it was IceCube completed in 2011, the first detection of astrophysical neutrinos in 2013, so 2 years after the completion. The method I mentioned to you, an excess of high energy everywhere in the sky. Then the first source that has been identified was TXS 0506 plus 056, and this was identified through the multi-messenger approach. So it was a high energetic neutrino seen by IceCube, advocated to the rest of the community, and then a counterpart seen with gamma rays, and then this triggered additional sources, and then IceCube realized that there were a bunch of extra neutrinos back in time. That was a flare of this source, but because of the trials that was not seen prior to that. So this is seen and known as the first identified high energy neutrino sources. And then a second one has been found by IceCube more recently, this galactic nuclei, but it's a different way because this was seen by an accumulation of events in the direction of the source. So I would tend to say that it was solely IceCube who could find this source thanks to the accumulation of events. But this is the second point source seen by IceCube. And then even recently, more recently, they have seen an excess in the galactic plane of events. And this was expected because we know that there are cosmic rays in the galactic plane that do interact with the material producing what we call galactic neutrinos. But IceCube was maybe not, optimized for that. I think KM3net is more optimized for that, but they have made the discovery before. So a great number of discoveries, more is to come. But after that, I will focus on KM3net. One final few slides on IceCube to tell you that it was foreseen over this winter season 25-26 to deploy 7 additional strings. So that was called, I think, the IceCube upgrade with the idea to lower even the threshold and to study atmospheric neutrinos. So in fact, I think what has been deployed is actually 6 strings that could be deployed over the season. And that was the major operation since, the completion of IceCube. Among the 6 strings, I think 5 are currently working, and there is an issue with one of them, but I doubt that it changed that much the sensitivity. And so this is really aimed at studying the neutrino, the tau neutrino sector of atmospheric neutrinos, I would say, with some sensitivity to the mass ordering, but somewhat reduced with respect to ORCA. So a recent great achievement about IceCube. So since they have such a successful story, why would we bother to continue in the Mediterranean Sea? The reasons are listed here. So I told you about the good pointing accuracy already. That is related to the transparency of the ice versus transparency of the deep sea water. But also we have deep sites close to shore in the Mediterranean, and that's good for the shielding against the atmospheric muons background. We have a nice logistic close to the shore, with in particular on the French coast, the French IFREMER. This is the Institute for Sea Sciences, very close to the detector site. Of course, it complements the view of IceCube, and so we really want to have detectors in the northern hemisphere as well. Another asset is to be at mild latitudes, because you can take advantage of the Earth's rotation to have over one day a larger view on the sky, so 3.5 steradian after one day, meaning that you may have some overlap with IceCube over the day. That's good. And then also you may use this in order to do on and off studies. So at the different times of the day, you're not looking at the same part of the sky, and therefore you can measure your background versus the region of the sky that you're willing to study. One drawback, but that turns to be useful actually, is the optical background that is coming from K40 decay. Because of the salty water, you have potassium decays into electrons, and the electrons pass the Cherenkov threshold. So you have all the time a lot of light that is seen, and we record all this light and we send all the data to shore. So you need to have a bandwidth. So the issue with K40 is not about the bioluminescence, which is a different story, or the fact that you have a large counting rate. It's just that you have to have a good bandwidth to then make causality filters. But we use that to calibrate the detector, because then you may ask for coincidences due to the local decay of the potassium. And then from those coincidences, you can measure your efficiency, the time of sets, and the time accuracy of your detector. So that turns out to be pretty useful. Okay, so I mentioned to you the first efforts that we did that were coming from ANTARES. So ANTARES was located at the French Riviera. So if you're familiar, you know the city of Toulon. Otherwise, it's just, the same, this area. This is the city of Porquerolles, and the detector was 20 kilometers south from Porquerolles. The cable was 40 kilometers long, and this was our counting station, sorry, very beautiful. We were installed at this place, actually, so with a splendid view on the sea, which I spare you not to, But unfortunately, we are moving to another place, which is on that side. It's okay still, I can tell you. Anyway, so really that is a nice place to go. In particular, that was not my motivation to leave D0, but I remember that we used to go on counting rates deep underground the building. Not quite the same. Okay, so the detector was the first detector of ANTARES was only a small detector, 12 strings, with 450 meter height, and triplets of photomultipliers for each story. And each of the strings had to be connected to a junction box, and the junction box was connected to the shore with a main cable. And so each of the strings were connected with interlinked cables. And so we have deployed that during 2008 and 2006 and 2008. And but we started, of course, earlier the first deployment. And so on this picture, you see the Nautile submarine vehicle. It's pretty known because it has been used to discover the Titanic and to go search there. So this is the submarine from Ifremer, and this is the version that we used in 2001 for the first deployment. And in 2022, when we recovered the detector, we also use it was refurbished since then, but it's a picture of Ifremer. And so these are the main steps. We installed the main electro-optical cable in 2001, then the junction box in 2002. We had prototypes from in 2002, 3, and 5, and then the first complete line was immersed in 2006. And then it took us 2 years to complete the detector, and then we have been running for quite some time. We were supposed to stop in 2006, but in between there has been a revolution, right? Because IceCube made discoveries of high energetic neutrinos, gravitational waves were discovered, and so we decided that we should keep running ANTARES to search for counterparts of neutrinos with ANTARES. So I'm telling you that we were running for 6 additional years without common funds. Essentially, we only had to pay the bill for electricity that was partly covered by KMPNet, I should say. So it's very cheap experiment to run, actually, and we've made the demonstration of that. Then when KMPNet was ready, we decided to stop ANTARES, the data taking, and to recover it. And here you see a few pictures of this long story that I tried to make short. So this is an old picture of the deployment on the junction box. I'm also showing you that to tell you that sometimes the weather is bad in the Mediterranean. It's not always like you could imagine. I doubt that under those conditions we could today make a deployment. That probably would not be allowed. But okay, all times, old-fashioned ways. This is the picture of the junction box in 2022, actually, 20 years after its deployment. It was unplugged, and there was no failure from the junction box. We had been waiting properly, and it's now waiting for potentially a second life, who knows, together with the main cable. And that's the first string that you see. And I'm showing you that also so that you can understand the size that it takes on the boat. It's still the same boats that we're currently using for our deployments. But you see that one string only could be on a boat. Now we want to put so many more strings that we had to compactify the approach. We immersed that during Valentine's Day. That's why you have this you have this heart, and that's why also you can see that this was line 1. And actually, those paintings remain for quite some time. This is a picture of the recovery to clean the plate in 2022. And this is the recovery of line 1, as you can well see from the art. And these are also the same people with some more white barbs, but essentially a similar team. So 20 years after. I just added back these slides because we had over lunch a discussion about hearing the waves. So I should let you know that ANTARES was really a multi-observatory, a multidisciplinary observatory. And so we have made publications on different aspects. And in particular, we studied the sperm whale gill behavior. So the only thing I can let you know about that is that sperm whales have lunch at midday, just like us. They dive, and so that's one of the conclusions of the paper. For the rest, I invite you to read that. These are different things, but pretty interesting for oceanographers. All right, so the future is KMPNet, or the present is KMPNet, I should say, and the future, hopefully. So this is now the collaboration. So it's still pretty much a European effort, and so you see the different institutes. But not only, so we have institutes in North America, in the US, that have joined recently, so at least three of them. And of course, the collaboration is expanding all over the world. In gray, these are associate countries, not yet paying the common fund. This is a phase, a step, but I hope that they will join. So we are growing. We're welcome to consider. So we have rethought the design of the detector, and so we came in with the concept of multi-PMT optical module that is now spread everywhere, including in the updates of IceCube and in P1. So the idea is to put small PMTs in a single sphere of the same size as the one we used to have for ANTARES. And of course, it's cheaper. You have more photocathode on a single sphere. In particular, on the upper part of your sphere, you have this photocathode, so you can reject the background. And then you can also play with the multiplicity of your kit phototubes in order to, well, to have a better directionality potentially. And also this is good for us for detecting MEV neutrinos. We are not meant at all to detect MEV neutrinos. We cannot reconstruct the trajectory at this energy. But if there is plenty of MEV neutrinos produced by a supernova, this will increase the multiplicity of the detector, and this pass a threshold, then it is going to be a 5 sigma discovery. So I have no time to cover that, but with ChemTreeNet, we have a 5 sigma sensitivity to any supernova in our galaxy, thanks to this approach. So we have two sites actually. We have one site that is dedicated for astrophysics. So this is the one that we call ARCA, for astroparticle research with cosmics in the abyss. And it's going to be made of two building blocks, 230 detection units. And the low energy branch is close to the ANTARES site. It's called ORCA, for oscillation research with cosmics in the abyss. That's the same technology, but it's a smaller detector in order to have a smaller, a lower energy threshold for atmospheric neutrinos. The depths are great in both sides, and also this, so this is a solution to some long-standing issue on the site where we would put ChemTreeNet, because of the fundings that comes from the EU has to be used regionally, and so that also helped us very much to settle a difficult question. Okay, so the ChemTreeNet infrastructure is shown here. So here you see the typical size of ORCA with respect to the building blocks of ARCA. So all in all, ARCA is going to be more than a kilometer cube. It seems that the Eiffel Tower was always used to calibrate the size of the detector, and this was introduced by IceCube, actually. But since we also have a site in Sicily, we put the Pisa Tower as well. So you can figure out, but anyway. And currently, we have 51 DUs, so detection units, strings, on the ARCA site, and 38 on the ORCA one. So the 6 last DUs were connected, I think, 10 days or 15 days ago. So it is growing, and we expect to have the completion of both sites by the end of the decade, hopefully. So we are on a pretty good path for that. So I'm afraid I'm running a bit late already, but you will tell me, and then I can skip some of the things. I would like to tell you, of course, about what we have been doing in terms of physics. So that's the scope of the physics we want to do. And I already mentioned to you the fact that we are sensitive to supernovae neutrinos. I'm not going to cover that anymore. Maybe I will touch the oscillation at the end of the talk, and then I will concentrate on the high energy astrophysics. But you should know that we're also an experiment meant to search for dark matter in an indirect way in dense sources where accumulation of WIMPs, for example, could be present and then annihilate, and in a subsequent approach produce the neutrinos. And so if you see an excess of neutrinos at high energy from the sun, that could be a signature of dark matter. And we also have exotic studies, like we study monopoles, nuclearites, and things like this. I think this is worth mentioning. I mean, this kind of experiment is pretty broad in terms of physics yield, and that, at least in my view, something that is attractive. I mean, the attractiveness of the experiment is something important for young people, for instance. So there is room for everyone. Okay, so final results for ANTARES. ANTARES was running for many years, but not large enough to confirm the IceCube astrophysical fluxes. But interestingly, we have been able to place limits, and those limits constrain a little bit the landscape. So these are the full ANTARES data that have been analyzed here. And this is the different limits that we have been placing depending on the spectrum, on the steepness of the spectrum. In fact, the conclusion of that is that the ice cube data and the ANTARES limit are not fully compatible, except if we put a low energy threshold. And essentially, we claim that there should be a break in the spectrum seen by ice cube, which is probably something that ice cube is seeing as well here. And so, in fact, you cannot have an hard spectrum that would be continued low in energy, that would be extrapolated lower in energy. It has to have some break at low energy somewhere. And so this is something that we have been able to publish. Of course, ChemTreeNet with its sensitivity to the diffuse flux will come and give you way more details on a short time scale, because we expect that combining the tracks and the cascades, we will have a 3 sigma in 3 months and 5 sigma in 6 months with respect to the ice cube diffuse flux. And then, of course, after that period, we will, this may come earlier because we're taking data along the construction, right? And it's not taken into account. But that's interesting. And then, of course, what we want to do is not only confirm the flux, but also study it into more detail, understand the steepness of the fluxes, the different spectra, the breaks, etc., and the flavor composition as well. Okay, focusing on the galactic plane, we have been able also to see a small excess with ANTARES already. And actually, this was published before the discovery of ice cube, but it's not a 5 sigma. It's only a 2 sigma excess that we have seen with ANTARES, both in tracks and cascades. So you see the small excesses that we have. And I was mentioning to you earlier the fact that we can use the Earth rotation to do on and off studies. So this is very simple approach that we have been following. We were targeting the ridge of the galactic region here. And so these bands are along the time where we control the background. So we just compare the measured background in the same direction with respect to the detector, but when the detector is not facing the galactic ridge. And so we have seen an excess, and this excess has been treated in terms of a signal, and then you see the contours in terms of intensity and spectrum indexes. That is of interest, of course. Here again, ChemTreeNet is optimized for that, and we'll tell you way more about this soon. With ANTARES, we also reduce the window for search and search for point sources. We haven't been able to identify any point sources, unlike ice cube. And our hottest spot on the sky is shown here, but it has very little significance after you account for the trials. But more interesting, perhaps, is the list of sources that we have been searching for. So you can use predefined sources and search into the direction of those sources. And so this is the sensitivity according to the declination that is seen here. And each of the triangle is our upper limit for the sources we consider. And so, of course, if you have an upper limit that is above your sensitivity, that means that you have seen a small excess. And so this is why those limits are bad, but they are interesting because behind there are a handful of events maybe. And interestingly, you find back TXS 0506 as a potential confirmation of this source as seen by ANTARES. The galactic center also presents a small excess. None of these are significant by their own, but you know, it's interesting to point them. And I wanted to let you know about that. So remarkable sources, I was mentioning TXS. Not only we have a small excess, it's very small because you see we fit 2.3 events, but it is a 2.4 significant. But that's also interesting to see that those events are not fully coming randomly. And in particular, we have one of those coming during the ice cube flare that has been seen for this source. And so that is also unlikely. So that's interesting that ANTARES has seen events in conjunction with the ice cube flare coming from TXS. I think that is enforces somehow the results of ice cube on this. And then there are a few other sources of interest that I will leave it to you for discussion afterward. Sure, sure.
Is that it's a flux?
Yeah.
Is that compatible with
Yes, it's compatible with what IceCube sees with the galactic plane, but IceCube has made a very different approach. They have been using templates of diffuse fluxes. We have done the same. And in our studies, we also see the template study. We also see a small excess. But this one, and so our limits are compatible with IceCube as well. The interesting thing, and this is why I think that we have to use ChemTrinet for that in the future, is that so we find back our excess with the templates, but the most significant excess from IceCube is seen with a template of pi zero, very simple, where you have neutrinos coming from pi zero. It's not a sophisticated, I would say, template, and this one is not very present with our current data. So I think that one has to understand where the neutrinos are coming, and there is not statistics enough to say something interesting. So I think this is coming with ChemTrinet, hopefully. But the overall excess is yes, is compatible. I speak about excess, but you understand me. Nothing is significant with ANTARES, right? It's just small excesses, but in the context of prior discoveries, it makes some sense. All right. And the prospects are very good with ARCA, of course, because we will gain essentially more than an order of magnitude with respect to ANTARES. And this is pretty flat sensitivity on all the sky. And in terms of galactic sources for which we are optimized to some extent, well, discovery should come after a few years. And if no discoveries are coming, then this is really going to be meaningful in terms of constraints on the physics that is happening with those sources that are seen with gamma rays. And so the gamma rays could be coming from pions or different scenarios. So this is also important. Okay, so to summarize what ANTARES has been doing, we have come up with a final paper called 2 Decades of Neutrino Searches. And so most of our papers or results are summarized in this paper, if you're interested. And now I should speak to you about the results that we published in Nature last year. So this is the observation of a ultra-high energy cosmic neutrino with ChemTrinet. So I'm sure you've heard about that. Again, the Eiffel Tower. Let me see whether I can, yeah. So here, this is what you see is the event. So, well, this is potentially the direction of the event. And then you see the ChemTrinet strings that were in place at that time, 21 strings only at the moment of the event that was seen in February 23. And so what you see, all these buttons, right, they are the lights seen from the optical module. Since you have 31 PMTs, we have those different things. So it is you can't really appreciate, but it's a huge illumination of the detector that makes it very special, this event, and well reconstructed. So in fact, 3,672 PMTs, so 1/3 of the detector, were triggered. And from this total amount of light, you can infer the energy of the muon, if you believe this is a muon that passed through, 120 PeV muon, and that would translate into a higher energy of neutrinos. You have to make an hypothesis on the flux for that. So assuming e to the -2 spectrum, it's 220 PeV. So obviously the error band is very large, because you don't have a good handle on the energies. That's not very calorimetric. But it is really a spectacular event. This is, as a function of the zenith and the number of triggered PMT, our event. And this is all the events recorded here. So it's still an outlier that we can see here, which also explains why it maybe was not seen at the very beginning, probably discarded. But taking a closer look, here what you can see on very distant PMTs with respect to the track, you can still see nice peaks reflecting the residuals of your feet. And so very good residuals, even though you're far away from the track, means that that's because of the small scattering of the light, but also testifies the very good reconstruction that you have behind this. So in fact, at this energy, you should not expect to see the neutrino has a vertical upgoing event, because neutrinos of that energy can't make it through the Earth. They would interact earlier. So it has to be an inclined, very inclined neutrino. And in fact, the direction that we have measured is 0.6 degree above the horizon. So reconstructing the trajectory, it means that it came from the region of Malta, actually, but it passed over Malta and went into the sea a bit after the island of Malta. But in fact, it's not only in the water, because in fact, the island should be somewhere there. And according to the direction, the event has to pass through the rock for a large distance. So there's no way a muon can do this. It would be fully absorbed. So it is not compatible with a muon in terms of atmospheric muon. It has to be a neutrino interacting closer to the detector. In fact, 100 PeV muon would at maximum go 45 kilometers in water. So imagine, of course, the rock you have to multiply by its density, right? So clearly it's not an atmospheric muons. Unfortunately, we advocate and we claim that we have a very good pointing accuracy with KM3net, but the precision that is mentioned here, about 1 degree, is worse than what we would expect. The reason is due mostly to the absolute calibration system that was not in place with this partial configuration of the detector. So that's a pity that we cannot reduce for the moment the angular uncertainty, but we have hope that putting the calibration system in place, we can reassess the direction with a better precision. And so, of course, make associations with known sources. So far, there has been no association significant. There's a list of sources, potential extragalactic, that we have studied. Also, authors, have studied their own, but there's nothing that is significant. So I will not spend more time about this. But we hope that in the future we can reconsider this possibility. In terms of background, I told you it can hardly be an atmospheric background. You would expect 10 to the minus 10 events per year from atmospheric muons in a 2 sigma region of the reconstructed direction. And for atmospheric neutrinos, it is 10 to the minus 4 events, 10 to the minus 5 essentially. So clearly, it's more likely to be of extragalactic origin, of extraterrestrial origin, and presumably extragalactic as well, because there is no sources with power enough in the direction from the galaxy. One feature that I wanted to show you as well, that I think is interesting and that advocates the fact that it is a muon, is that at those energy, the energy losses of the muon are stochastic. And from time to time, you have huge energy losses. And we can actually see those along the track because of the very small scattering. You can see the different places where we believe that the muon has been releasing energy as expected. And so I think this can hardly be achieved in the ice, but in water, this can be seen. So this is also a good proof that it's a high energy muon. Okay, now what is puzzling is that such an energy has not been seen by IceCube before, and that puts the things into tension somehow, because this is our event with the statistical errors. It's a factor 30 above the highest energetic event seen by IceCube, and so of course it's somehow puzzling. Also, you see that it lies above the limits from IceCube and Auger at very high energy, though the error is large, and therefore, in fact, if you address all this together, the tension is only about 2 to maximum 3 sigma. And this is what has been shown in this article. In this article, they have taken into account IceCube and Pierre Auger observations, and also and these are the contours at measurement from IceCube into different samples, and this is compared to the KM3net band allowed band at 1 sigma, 2 sigma, and 3 sigma, and this is the limit from Auger. So if you put everything together, yes, there is some tension, but it's only something about I would say 2 sigma. If you let everything unconstrained and you make a joint best fit, then this is what you would obtain considering the other experiment as well. So one scenario is that the origin could be a cosmogenic neutrinos. I mentioned that to you earlier. It's not completely simple, however, because you have to consider that potentially the evolution of sources, so that's a bit technical, but it will probably speak to some of you. These scenarios of sources were considered with close-by sources, but you have to consider somewhat different evolution of sources. And if you add, in addition to that, a subcomponent of light nuclei, like protons, then you have increased fluxes that are shown in yellow here. And so that is more compatible, and it's open scenario, with the measurement from KM3net. So that, to some extent, advocates somehow a sub component of light element, but with an evolution sources higher. So that has also been published if you're interested about those details. Okay, I'm not done, but almost. How bad am I? Am I already done? Yeah, okay. No, I'm fine. I'm happy with questions actually. So just to let you know that we've done these multi-messenger games with ANTARES a lot. We have received alerts and look for events. We have not been able to find anything. We also sent our own alerts to the rest of the world. And only once there was something very interesting, but it turns out to be a fake coincidence. But okay, this also summarized in our legacy papers. And finally, I would like to tell you a few words about what we want to do with ORCA, which is, as I told you earlier, measure the mass ordering with atmospheric neutrinos. Why can we measure the mass ordering with atmospheric neutrinos? The reason is that the oscillations in vacuum are not sensitive to that, but in the matter, you have resonant effects. And so this will alterate, modify the amplitudes and the frequency of the oscillations. And this modification depends on the sign of delta M3. And so this is how you can get access to the, but it's a very tiny effect. And I should also say that this effect is symmetric with neutrinos and anti-neutrinos. So you expect the same feature with neutrinos and a sign of delta M3 than with anti-neutrinos and the opposite sign. So that way, if this is symmetric, there should be no reason why you could detect them if you are not able to distinguish between neutrinos and anti-neutrinos, which we cannot because we have no magnet. But the reason why we have access to a net effect is that the cross-section in the GeV domain where we're looking at is not the same for neutrinos and anti-neutrinos. Also, the flux is a little bit different. So plugging all this into consideration, you have a net effect on the mass ordering. And this effect is summarized here. So depending also on the value of theta 23 that I told you, we don't know about it. We don't know if we are in the second octant or the first octant. Depending on this consideration and depending whether the ordering is normal or inverted, we could reach in 3 years 5 sigma almost of ORCA, or we may have to wait longer. Of course, we can do additional physics than that with ORCA, in particular, measure the different contours, the different parameters with more precision, and we expect to do so. One way to get to a result on a shorter time than running only with ORCA is to take the advantage of the synergetic, I don't know if this is proper word, of the combination between what we can do with atmospheric neutrinos and the Juno experiments. So I guess Juno, you know what it is. It's a reactor neutrino experiment currently taking data. And so they are looking at the wiggles of oscillations into reactor spectrum. The reason why there is a synergy is that if you make a wrong assumption on, if you combine your data and you make a wrong assumptions on other parameters or on the ordering, then you will measure a wrong parameter, one of the other parameters wrongly. And so making a wrong assumption somewhere will turn out into a disagreement in other parameters. That boosts your sensitivity to the mass ordering in a spectacular way, as you can see here, because this is what we expect with ORCA alone. And this would be the combination with Juno, and this is Juno alone, depending on the time. And this is true for the normal and inverted hierarchy. So with that, we can imagine that having the combination with Juno in the coming years or the years that are coming, we should have a hint maybe on the mass ordering. And just to finish up with the projections, this is ORCA. and this is compared to the rest of the experiment. So here, this is where we are, right? With ORCA. ORCA would continue like this. ORCA with Juno will have this boost, okay, against time. So, and then this would be Juno alone, again shown, and compared to the Ice Cube upgrade. So you have to consider a band because of the degeneracy of the parameters that are not measured like this. But this, I hope, means that we should be able to have a result by the end of the decade. That's very an important measurement. And just to tell you that we have started to study all these things. So this is the results that we have had with the 6 only first strings of Kouchner. And these are the contours that we have. They are not spectacular, but they are compatible with the rest of the measurements. And 6 strings is, of course, small. We will have new results at the neutrino conference this summer. Right, and of course, we can study more than the mass ordering. And if you're interested, you have here our latest publication on the expectations of ORCA on neutrino physics. Okay, and so I will conclude here. Thank you very much for your attention.
Thanks for a fantastic talk. Are there questions?
I hope there are questions. That way I have time to show you this movie and we can discuss along the movie. Oh, that's not a movie. That's the movie of our deployment procedure. And so we can chat over that. You have seen that.
All right, questions for Antoine?
I have a very simple question. For that last piece of analysis you were talking about, how dependent on it is systematics related to modeling cosmic rays in the atmosphere to get like the intrinsic neutrino flux, or is that something you're able to fold out pretty clearly?
For the mass ordering, you mean?
Yeah.
So for the mass ordering, we have a lot of systematics that we have to account for. Systematics are coming from the neutrino flux. That's true, but I don't think this is the most important one because the measurement is a measurement that you want to compare region of your zenith angle and energy against others. So this balance somehow the problem of the systematics, but you have more systematics that come from the unknown on the cross sections, the efficiency of your detector, of course. Also, it's true that the ratio of, how to call it, the polarity of your neutrinos and anti-neutrinos that play the game, it's not fully, so that relates more to what you mentioned. So they are all considered a priori to a good, to a fair effect, and so I think they are accounted for. I think that related to the systematics of these measurements, what is more important is probably the energy scale, because you really want to, so the direction is something that you better control, but the energy is more complicated. And so you have to make sure that you properly measure the energy of your events, because it's really the oscillation pattern is energy against zenith. That is probably the key the key thing here. Yeah, so you have seen those different I don't know, frames. So this is encompassing a full string, and so we could put 6 on the same boats with respect to the very long ANTARES line, and then it's going to unfurl automatically when it's we release, and so we recover the frame afterwards, and we can reuse it to deploy several strings. So that means that when we have a C campaign, in principle, we are able to put at least 6 strings in a row, depending on the weather, but usually, and even more.
You spoke to the complementarity with IceCube with data train app. I'm just wondering, like Lake Baikal, P1, China, like what would be, the benefit of having all of those kind of turned on and working together?
Right, more photocathode, more neutrinos. That's the basic answer. Then, of course, I don't think that you want to place that in various places. So, of course, you should. If you put them in the same places, you don't gain much except for this additional extra numbers of neutrinos. And since I told you, depending on the zenith, you cover a different energy range. So typically, the TV domain is the one that you have by upgoing particles. and hundreds of TV, and PV is going to be on the horizon place, and perhaps you can reach higher energy or the same energy with downgoing fluxes. So you want to play with the different locations on Earth to cover instantaneously different regions of the sky. So I think it has some sense at different time if you want to see, if you don't want to miss events. Having said that, to my knowledge, there has not been any discoveries instantaneously, meaning by that you know the event says this was a counterpart seen for a long flare. We have not been able to see GRBs together with neutrinos so far, or gravitational waves together with neutrinos so far. So on a short time window, there was nothing. Well, it's of course important for supernovae, but it's completely different game here because you don't set the trajectory. Anyway, the Chinese efforts are ongoing, and there is a major difference here, is that they are not planning for a kilometer cube. They are planning for way more than a kilometer cube. Of course, they are planning to the next generation. So the way I see things is more that the Chinese efforts are the next generation, and maybe everybody will have to consider constructing a very big detector there. P1 is essentially at the stage of ANTARES 20 years ago. So it's about testing a site, but on a different location. And I think that the goal is to have a kilometer cube detector, right? So that's my understanding. But first, it has to make a demonstration with a small array. So let's see what comes out of this. And then Baikal, it's annoying because I think, to me, you know, they are doing great things, great physics potentially with their detector, which is not published. You know, it's not sufficiently published and advertised for reasons that you understand. While the detector is coming to be huge, there are disadvantages of being in Lake Baikal because it's known for a very beautiful and clean water, but the absorption length is actually way shorter than the one you have in the sea. It's about 20 meters, I think. So it's very clean water, but it's actually not a very clean environment because it's a closed, place, and so there's no circulation maybe. So you may have more mud, etc. So the water properties of the lake are different. That doesn't prevent from constructing a very big detector. But yeah, essentially it's a pity, and they have indication of a confirmation of the ice cube fluxes. So they have nice results. But the fact that we don't really, you know, for instance, ANTARES and ice cube, we have made common publications. I never succeeded to do the same with Baikal, and prior to the war in Ukraine. So it's also more complicated to collaborate, I would say. They initiated the efforts for neutrino astrophysics a long time ago. So it has somehow always been like this, that the cooperation was less smooth than with ice cube.